What is fire? Can you touch it? Can you grab it? Can you hold it? Not really. So what is it? So there's a famous essay from the 19th century. So a photon is a packet of energy, of pure energy. It moves at the speed of light. It's the only thing it knows how to do, is move at the speed of light. And so by the way, energy can manifest in many different ways, okay? You can have potential energy. Why is it that you can harm yourself by jumping out of a window? There's a reason for it.
Okay.
Because when you hit the ground, energy killed you.
I thought it was the sidewalk.
Okay. You had energy in your body.
Yeah.
While you were falling.
One Red Bull right before the show.
Right. And yes. And the energy kept accumulating as you fell faster and faster.
Right.
Then you hit the sidewalk. All the energy that was in you from your motion, kinetic energy, goes back into you as mechanical energy. And the only way your body can accommodate mechanical energy is to break stuff, because it takes energy to break your bones.
Sure.
Energy can manifest in different ways. And the higher you take the elevator before you jump out the window, the more energy you have to break your bones upon hitting the sidewalk. That's why jumps from higher altitudes will do more damage than from lower altitudes.
But if you're watching this and thinking about it, don't do it.
Do not try this at home.
Don't do it.
Now, above a certain height, there's an air resistance. You hit what's called a terminal velocity, where the air is absorbing away some of that energy.
I am about to terminate. Be terminated.
Terminal velocity to be terminated. So there are other ways that energy can be stored, like inside of an atom. And an electron can sit in many different energy levels. The atom has energy levels within it. It's not a continuous placement of energies. If there's an electron at a higher energy level and something happens to make it drop to a lower energy level, it just lost energy. Where did it go? Actually, it can go in one of two places. If another atom hits it, some of the energy of that electron can go to the kinetic energy of the other atom as it careens off. Oh, this happens a lot. So it's a kinetic energy.
Mugging.
A flyby looting of its
That's
energy.
right.
All right. So, but occasionally it just sort of jostles it. The electron de-excites, goes to a lower energy level. Where does that energy go? Bada bing. A photon is released from the atom of exactly the same energy as the difference between the energy levels of the electron. All the energy is accounted for. And the photon goes in a random direction at the speed of light. That's where photons come from. They come from ways that used to be energy in an atom or the vibrations of atoms and molecules and other particles. And in those vibrations, it can lose energy by releasing a photon. And that's what's going on.
I have a last gap to fill with gravity. If gravity is the effect of the mass bending space, then why, when a star goes supernova, is space still bent for a black hole to form instead of immediately unbending? It is as matter is blown apart, or better said, what makes space remember what was there before? So when it blows and matter is dispersed, space won't recover back, but stay bent as a black hole. Did you get all of that?
Wow. Stars above a certain mass, when they die, will go as supernova, and they'll leave behind a neutron star. Stars of even higher mass, we're not entirely certain of the boundary of this, but stars of a higher mass can go supernova and make a black hole. Stars of even higher mass, the supernova never gets out. Black hole all the way. So only in that last case is all the mass of the entire system part of the black hole. And the space-time curvature at the end was the same as it was in the beginning. Whereas the one where some gets blown out and others become a black hole, yeah, that black hole does not have the full gravity that the whole system had before, because half of it got blown away. It's that simple. So he's right to think about this, but the answer is not that deep.
That's pretty good.
Okay.
Yeah.
Mm-hmm.
Matthew Jury wrote, hello, everyone. How can a gravitational singularity exist if infinite curvature means infinite time?
We do not have a good way to talk about the singularity.
Would you say the jury is out?
What I would say is that's why we have string theorists. To bridge the gap between quantum physics and general relativity, one, the theory of the small, The other, the theory of the large. But at the beginning of the universe, the large was small. Whole universes were operating in the quantum realm. And
I've seen Ant-Man. I get it.
yeah. Well, there you go. Okay. So if that's the case, what's happening at the singularity? Because you don't get singularities in quantum physics, you get it in general relativity. So that's where it's been said the singularity is where God divides by zero. Have you divided by zero lately?
Error.
Yes.
Yes.
Error.
I do a magic trick where I have people put stuff into a calculator, and if they divide by zero, there's no magic trick because there's just an error. So I very much, it's very salient for me
Wow. Okay.
to avoid the divide by zero.
If you divide by zero, it's an error. It's undefined. And we don't know what to do there. Yet we know these two theories work in their own realm, their own regimes, the small and the large. You bring them together, it's a shotgun wedding that won't necessarily work as you had planned. So we got top people working on it. So no, we can't tell you what's happening inside the singularity.
All right.
It remains a mystery. Yes.
If someone keeps traveling back and forth at Planck length distance, does it mean that it's traveling eternally? He did put a parenthetical which says an idea/attempt to say that the particles don't come in and out of existence. They are just traveling eternally at Planck length distances, and four forces hits them at the right time to let them exist in this universe.
Okay. Yeah, I don't know what he's talking about. I can tell you this: a Planck length is the smallest unit of length that we can measure. It's very, very small. It almost doesn't make sense.
It's not the size; it's what you do with it.
It turns out in quantum physics, everything is in motion. Everything vibrates at all times. So
Exhausting.
to say you have something moving back and forth across a Planck length, all matter is doing that at all times because everything is always in motion. Always. So to say, let's do it at a Planck length and it's time at infinity, I don't know how the connecting Planck length and infinity time in that question, but everything is always in motion at all times. And it has nothing to do with measuring time at infinity.
I was just wondering why black holes can't just be dark matter. There seems to be a lot of them. They are massive and seem to have more gravity. Most importantly, we can't see them.
Let's list the dark matter candidates. Would there be dark clouds? Could there be vagabond planets that are not illuminated by a host star that got ejected into the galaxy? Could it be black holes? It turns out the physics of the early universe limits how much ordinary matter there can be. Black holes count as ordinary matter because you make them from ordinary matter. It limits it. There's a delicate set of knobs that we're turning in the early universe to understand what the universe was and what it became. And so these knobs they're fascinating because some combinations of knobs don't work at all. You don't get a universe, or you get a universe that's very different from what we have. So the problem with dark matter is it doesn't interact with ordinary matter in any way other than by gravity. And so if you look at what it does in the universe during the early universe, it can't be regular matter. Otherwise, we'd have a universe completely different from what we have. And black holes are made of ordinary matter. It has to be something completely exotic beyond the measurements we've made of electrons, protons, neutrons, atoms, molecules, solids, biology, chemistry, physics, psychology. Everything that we know and love falls outside of what dark matter can be. So let's say we have very good theoretical evidence, theoretical support for why dark matter can't be black holes.